So I'm going to do two sets here. I'm going to do the set that starts, let's say, right here. So at -2, including -2, and then we'll go up to 1, including 1, and then everything in between. And then the second set is going to be -2, so a point here, a point here, a point here, and a point here. Are those the same set? No. So visually, it's pretty clear that they're not the same, right? Because in the second one, we're skipping all of the numbers in between the integers. So integers are your counting numbers like 0, 1, 2, 3, 4, 5, and then also the opposites of those. So no decimals or fractions. So in the first one, we are including every single number in between those integers, whereas in the second one, it's just those 4 values that are in the set, right? So we call this guy a continuous set. Because going from the bottom number to the top number, like I don't have to like jump around at all, right? I don't have to skip anything. I can just, it's a straight shot. And then we call this a discrete set. So if we were just thinking of this like in terms of like plain English, we might describe both of these as like all the numbers from -2 to 1, right? But mathematically, we of course want to differentiate between a discrete set and a continuous set. And so when we write this in set notation, we have to have 2 different ways of describing these sets so that we don't accidentally say that they're the same thing when they're not. So for continuous sets, we're going to use interval notation just like we did last week. So the smallest number in that set is -2, which I want to include with a hard bracket. And then the largest number is 1, and then also including that. Anytime you use interval notation, you are assuming that every single number between the smallest and largest is included. You can't write an interval that skips a number somewhere in between those 2 values. You would have to do separate intervals, which we'll look at in a minute. But the assumption is that that notation means every single number between -2 and 1 is in the set. And then for discrete sets, really the only thing we can do is just list all the numbers that are in the set, which can get a little tedious sometimes if there's a bunch of them, but luckily here we just have 4. So we use curly brackets to show that we are writing a discrete set, and then the numbers that are in that set are just -2, -1, 0, and 1. And because we use the curly brackets and listed the elements of the set, that's what tells us that we're not including the numbers in between the ones that we listed. So even if we had a set that only had 2 numbers in it, it can look a lot like interval notation if you don't use the right brackets, right? You got to use those curly brackets. That's what tells us it's not from here to here, it's just this one and this one. Does that make sense? Okay. So now let's look at what happens if we combine these. So you can combine any sets you want into a single set just by using what we call a union. So the union symbol it looks kind of like a U. So if I had a set, we'll graph it first. Say so let's say -1 and everything less than -1. And then maybe I just have a point like up here. So if I want to describe everything that's in red on that number line as a single set, well, there's no way I can do a single interval that includes that point, right? Because if I were to say there's no smallest value and then go up to 2, I would be accidentally including all of this, which I don't want to do. So the only way to do this is to do both an interval and a discrete set and then just put them together. And when I say put them together, like all I mean is like put the union symbol between them. So we're not actually doing anything to put them together into a single statement. We're just connecting them. So there's no smallest element of the set. Remember that when we do interval notation, we are walking from the left to the right. So the leftmost number in your interval notation has to be whatever is furthest left on the number line, and the right one has to be the furthest right on the number line. So in particular, you will never have negative infinity on the right side of an interval. Like, that's impossible, because negative infinity is the arrow that points all the way to the left. It will always be on the left side. And then vice versa for positive infinity.
-1 soft bracket?
Yes. -1 soft bracket, because we're not including it. And then for that single point, I need a discrete set, right? Because I can't say that that point is between here and here, right? I can't do an interval to describe a single point. And so just that point is the set containing only the number 2. And then to make this into a single set, we just put the union symbol between. So far, so good? Another one we'll see fairly often is when we just like skip like a single number. So instead of having individual numbers that are in the set, you can have individual numbers that are not in the set. So for example, let's say all numbers except 1. So essentially we're saying everything up here and everything down here. And then we have an open point at 1 to show that we're not including 1. But we don't typically use these open points anymore, right? We use our brackets. So what we've essentially done here is divide my number line into 2 intervals, right? So it's everything up to 1, but not including 1. And then we start out again infinitely close to 1, again not including it. And so we can think of this as like 2 inequalities. This is all of the numbers that are less than 1, and this is all of the numbers that are greater than 1. And if we put those 2 together, we have included everything on the number line except for the number 1. So in interval notation, is there a smallest number in this set? There's not, right? The arrow is shaded going left. So negative infinity. But I can't go up to positive infinity, right? Because that would include 1. So I have to stop at 1 and not include it. So that's the set x is less than 1. And then I'm going to start up again on the other side at 1 without including 1. And then there's no largest number in the set. So all I did was just like jump over the value 1. So I got infinitely close to it, skipped it, and then started up infinitely close to it again. Note that when you're skipping individual numbers like this, you can never ever use hard brackets, because if I put a hard bracket right there, that means that 1 is in the set, right? That's just the set of all real numbers. I haven't skipped anything because I included the 1 in one of my sets. Or if you did it in both, the same would be true. So if you're skipping a value, it always has to be a soft bracket, because that's what tells us we're not including it. So you'll never have any hard brackets on those. What do you think it would look like if I skipped like 2 numbers? Like, what if I wanted all real numbers except like 1 and 4. So start by drawing that on the number line, and then see if you can figure out what the interval notation would look like. So this is going to look exactly like the one above it, except that whole back-to-back soft brackets is going to happen twice, right? We're going to skip over 2 numbers. So we are not including 4, and we're not including 1, which means we've broken our number line up into 3 intervals this time, right? So it's all the numbers that are less than 1, not including 1. It's all the numbers that are between 1 and 4, not including either one. And then it's all the numbers that are greater than 4, not including 4. So every time you skip a number, you just break your number line up into like different pieces. And so depending on how many numbers you skip, that'll determine how many pieces you have. So then there's no smallest value. We go up to 1, don't include it. Start up on the other side, go up to 4, don't include it. And then all the way up to the top. Probably the most common error on these is skipping the 1 to 4 piece. Like you can't just go up to 1 and then start up at 4 because then you skip that whole middle section, right? So just kind of a general thing to remember is that every time you're skipping an individual point, your interval will stop and start at that point, right? You're not going to like jump from 1 to 2 over that union. And then the last example I wanted to show you, just so you have it, is probably the most common one, which is the set of all real numbers. So if I shade the entire number line, then there is no smallest number in this set, right? So we start at negative infinity, and there is no largest number in the set, and we are not skipping anything. So we're just going straight through all the way to infinity. This is the set of all real numbers. And symbolically, it's written like that. So double vertical line and then capital R. I just want to show you all the different ways you might see it. So like if your answer is all real numbers and you want to write it in an interval notation, you just do the negative infinity to infinity. I'm happy for you to use the symbolic notation, this guy right here, to express all real numbers. Like, you don't have to write it in interval notation, but I know in your homework, like, that comes up a couple times. So I just wanted you to know what that looked like. Any questions so far? Does this make pretty good sense? Yes?
So when would we use
The domain of a function is the set of all inputs for which the function is defined. So when we say something is defined in math, it just means it basically that it exists, right? So if we're looking at a graph, the function is defined for all x values that correspond to some point on the graph, right? So if I have a graph, like if I'm looking at this one right here, that is not defined for 1, right? Because 1 is not part of the graph that I've shaded there. But it is defined for all the other ones because if you pick any other number, that's part of the shaded region. There is a point in the shaded area that corresponds to that value. So the same is going to be true in 2 dimensions. The function is going to be defined for any x value that actually corresponds to some points on the graph. And then, well, we'll talk later about what it means in terms of equations. We'll just do graphs for now. So what is the range?
0 to
So it's the set, we're not there yet, just in general. It's the set of all all outputs of the function. Notice that individual inputs and outputs are not domains and ranges. Like the domain is the set of every single thing I can put into the function and have it make sense. And the range is the set of every single thing I can get out of the function. So like individual inputs and outputs are elements of my domain and range, but they're not, like we can't say the domain is the X value. The domain is all of the X values. So it's a big set that contains everything we can use. So let's start by doing this graphically, and then we'll do it algebraically. So your first, hey Gannon, I have a little piece of paper for you. So our first example is a discrete function. So we call it a discrete function because it's defined by individual points. So just like those discrete sets we just looked at where they just list the numbers that are in them, here there's just individual points that define the graph, right? Nothing is connected in between the points. And so when we find our domain and range, we're really just listing all of the X values and all of the Y values that correspond to those 1, 2, 3, 4, 5, 7 points. So our domain in this case is going to be a discrete set. So it's the set of all the X values. So -3, -2, -1, 0, 1, 2, 3. Right, so this is the point -3, 4. So that's where I got -3. The second point is the point -2, 2. And so this is in my domain. So those X values are the only X values that actually correspond to points on the graph, right? If I picked a different X value, like this guy, there is no point on the graph that has that X value. And that's why it's not in the domain. So you guys write down the range. Remember, the range is the set of all outputs. So in this case, that means the set of all Y values. I can leave that there. So what's my range? So -4, -2, 0, 2, and 4. Good. And note that we don't repeat any values in the set. So even though there's more than one point that has a Y value of 0, once 0 is in there, it's in there. We don't have to specify how many times it actually shows up on the graph. So sets are really just like you're throwing everything in the pot. And as far as order goes, like in discrete sets, the order doesn't matter at all. And so, I mean, it's nice to put it in numerical order because we all like things to be orderly, but the order that you put those numbers in doesn't affect the set in any way. Are we all clear on how we got both of those? Okay, let's look at a continuous graph. So when we look at this graph, every single point on that curve, I can pick any point I want, and that is a point that corresponds to an input and an output of my function. So we can see already there's an infinite number of points here, right? That's how you actually make a curve or a line, is it's just an infinite number of points stuck infinitely close together until they form something solid. So in this case, we're going to have to use interval notation rather than discrete sets because there's no way to list all of the X values that show up on that graph. So when we do continuous graphs like this, when you find the domain, you're looking only left to right because we're only thinking about X values. So you kind of have to think of these like in pieces, right? So like you don't care at all about what's going on up and down when you're finding the domain. You want the smallest x value to the largest x value. So my domain, is there a smallest x value?
No.
There is not, because I have an arrow that points left. And so we start with negative infinity. And then what is the largest x value? So it's at this point, but that point doesn't actually exist, right? So there isn't actually a point that has an x value of 3 because it's an open point. And that's one of those tricky things is visually we see it and we're like, it's right there, that's a point. But if it's an open point, that means the point itself doesn't actually exist on the graph.
So a 3 and an open, or
Yep.
soft bracket.
And a soft bracket, right? We can't stop at 2 because we don't want to miss all this stuff.
Yeah.
So that's why we have those soft brackets, is so that we can get infinitely close, but then not actually get to that point. So far, so good? And one other thing that didn't apply here, but we always want to check for, is if there's any gaps between the lowest and the highest, right? So if you make any horizontal jumps, right? If this graph were to, for instance, have a point right here and a point right here, there's no point on that graph that has an x value between -1 and 0. Right? If I pick a number right here, I never hit the graph. And so that's a horizontal jump. I've skipped x values, in which case we would have to do the interval from negative infinity up to -1, and then another interval from 0 to 3. Does that make sense? So you always want to look for horizontal gaps when you're doing your domain. It's usually pretty obvious if there's going to be one, right? When we look at this initially, like there's no breaks in that graph at all. So we don't have to worry about skipping things in between the smallest and largest. And then for range, we're going to do the same thing. Now, when we read from the top of the page to the bottom of the page. However, remember that interval notation goes from the smallest value to the largest value. So when we find range, we're going bottom to top, right? Smaller y values are on the bottom, bigger y values are on the top. And so we always want to start at the bottom of the graph with the range. What's the lowest point on this graph? So the lowest y value. I think I hear -3. Yeah? Is that included?
No.
It's not, again, because of that open point. And then highest point?
Infinity.
It goes to infinity, right? Because there's an arrow pointing up. Anytime you have an arrow pointing up, no matter what else is going on, it goes to infinity. I know that there was like one in the homework on my math lab that like the arrow was like down here, which I find to be super misleading because the arrow is like below another point on the graph. But even in that case, it would still be going to infinity because they put the arrow there. They just did kind of a crappy job of drawing it. Any questions so far? Okay, let's do this last one. So this one kind of brings in that question of gaps in our domain and range, right? So like, are we skipping any x values or y values? Because this graph is made up of separate pieces. So it's entirely possible that like we skipped over some values. So we have to be aware of that as we find our domain and range. So let's start with just smallest and largest, and then we'll think about if there's any breaks. So is there a smallest x value here? Right, there is no smallest x value, so I start all the way at -infinity because I have an arrow pointing left. And then if you walk along that line, do you skip any x values? So if we walk from left to right, are we going to skip any x values?
No.
We're not, right? Because the only breaks are actually, like, the only jumps are just vertical jumps, right? So I'm going all the way to this point, and then I'm jumping up to this point, but I didn't skip any x values in the process because I didn't jump horizontally, right? I just went straight up. And then we're walking along here, and then again, there's a jump, but it's not a horizontal jump, it's a vertical jump. So I haven't skipped any x values. Yes?
So if the longer one that loops down, if that were to have it open and it'd be open up there, then it would, right?
Yeah, if this was an open point right here, then we would skip the value 1, right? Because there's not actually a point with an x value of 1 if both of those are open. Good question, thank you. So then, yeah, since we didn't skip any x values, we have an arrow to the right, and so we're going all the way to infinity. So it's really tempting when you see, like, these, we call them piecewise functions, to, like, want to do multiple intervals. You just want to be really careful that you're only thinking about it in the horizontal direction when you're doing the domain. So, like, and again, like I said, sometimes it feels silly to, like, trace, but, like, really just, like, tracing from left to right is probably the best way to do these because you hit every single point. And, like, if you have to pick up your pencil to, like, jump horizontally, then you're like, oh, I just skipped some x values, right? So, like, actually physically following the graph is a good way to make sure that you've included everything you have to include and not included things that you don't want to include. So then let's talk about the range. We're going to do the same thing. We're going to go from bottom to top. What's the lowest point on my graph? 0. You think we should include 0? Yes. Because, so the only time you won't include a low or high point is if there's actually an open point. So it is implied that this is a closed point, even if we don't draw a closed point there. The only time you'll have those soft brackets is if one of your endpoints is actually an open point. Like, you don't have to worry about, like, oh, did we get infinitely close to 0 there but not actually touch it? Like, there's actually a point there. And you can make that assumption every time. So we're going to include 0. And then if we work our way up the graph, do we skip any y values? One way to see it on this one is just this piece of the graph alone covers every y value between 0 and infinity, right? Like, there's no vertical breaks in just that piece. Like, there's some other stuff going on over there, which means we repeated some y values, but there's no break at all in just that piece. So that covers the whole thing. If it didn't, like, if this guy didn't exist, then there would be one gap in this graph. Where would it be in terms of y values? Between 1 and 2, right? This gap right here, there's no part of the graph that has a point in that area, right? That corresponds to those y values. But, like, over here where there's kind of another break, or between here and here, like, these guys still exist, even though they're, like, on another part of the graph. So you kind of, like, have to jump around. But a good way to tell if you think that there is a gap in your domain or range is, like, so if I look at this and I'm like, oh, I think that there's a gap between 1 and 2, just pick a number in there and be like, oh, look, it intersects the graph right there. So there is a point that has that y value. So if you think that there's a point that doesn't correspond to a point, or if you think there's a y value that doesn't correspond to a point on the graph, just draw a horizontal line at that y value and, like, verify that it doesn't actually touch any point on the graph. Does that make sense? So you can kind of check to make sure if you have, like, the inkling that maybe you're trying to skip something. So in this case, we go all the way up to infinity. Because the domain and range, like, all they do is they tell you what numbers are in there. Like, they don't tell you anything about the shape of the graph or how the x and y values correspond to each other. And so it sort of seems like we're oversimplifying when we do this, when we're like, oh, we just go from 0 to infinity when all this other stuff is going on. But the domain and range themselves, all they do is tell us what numbers you can put in and what numbers you can get out. It doesn't tell us anything about how those things correspond to each other or what it looks like when you graph the actual function. So it's just all the x's, all the y's. Does that make sense? Cool. So we're going to change gears a little bit from graphs to algebraic representations. So in reality, finding domains algebraically using the formula for the graph is really what we do most often. Now that we have technology, it sort of sometimes gets like backwards. Like people will see an equation and graph it and then use the graph to find the domain. When in reality, the whole point of finding the domain is to help us figure out what the graph looks like. Like if we have a function, like a formula for a function, and we can find the domain, then we know where the graph is going to be, right? So what points are going to be on the graph. So more often than doing this graphically, we start with the equation for a function, use that to find the domain, and then that starts to give us an idea of what the graph is actually going to look like. So remember again that we do not have graphing calculators on tests. So if you're about to zone out because you think you're just going to put it into your calculator, that would be a bad idea. And again, like we talked about yesterday, you miss out on a lot of like the conceptual understanding if you zone out and don't think about it. So let's just start with an example. So finding domains algebraically. When we find domains algebraically, what it really relies on is just our understanding of like how mathematical operations work. So what we're asking ourselves, if I wanted to find the domain of, for example, f of x equals x plus 2, well, remember that functions are just like a set of operations. It's just a rule of what to do with your input, right? So this function says add 2 to the input. That's the rule for our function. So if we want the domain of the function, what we're asking ourselves is what numbers can I add 2 to? I should not have used 2. 2 is going to get really annoying. What I'm asking myself is what numbers can I add 3 to? So to sort of orient yourself on these, it kind of helps to break it into like 3 possibilities, like negative, positive, 0. Like, can you add 3 to a negative number? Can you add 3 to 0? Can you add 3 to a positive number? So you can add 3 to anything, right? And when we ask the question, can you do it, what we mean is like, do you get a numerical result? So when we say that an operation is defined or undefined, what we're saying is that if it's defined, we're saying that when you do it, you get a numerical value out. We're all familiar with like the term undefined in terms of like dividing by 0, right? What that means when we say division by 0 is undefined is that when you divide by 0, you don't get a number. Like you don't get any numerical value as an answer, and so it's undefined. So when we want to know where it's defined, we're looking for numbers that you can perform the operation on and actually get a numerical result from. And in this case, you can put any number into this function and you're going to get some number out, right? So this is defined for all real numbers. So when it comes to finding domains algebraically, all we really have to think about is what operations are in the rule, and then what numbers can you do with each of those, or what numbers can you do each of those operations with. So we're going to start with just a list of operations we know and write down what we know about them. And then we can use that to generalize how we're going to find domains. So we'll start with, well, we already did addition. So the operation of addition is always defined for all real numbers because there is no number that I can't add to another number and get some result from it. So defined for all real numbers. I'm going to use the shorthand, that symbolic shorthand, just because I'm about to write that statement like 5 times. And I don't really want to write it 5 times. So an example is just the one we just did, like f of x equals x plus 3. The only operation in that function is addition, which means the domain of the function is all real numbers because that operation can be done with any number. Does that make sense? What about subtraction? Are there any numbers like you can't subtract? So for example, if I had f of x equals x minus 3, like I can plug a negative number in there and that makes sense, right? I can plug a positive number in and it makes sense. I can plug 0 in and that makes sense. So there's not any number that I can't subtract 3 from and have it make sense. So again, subtraction is defined for all real numbers. The good news is that most operations are defined for all real numbers. There's really not that many restrictions. It's funny because when this is taught, people focus so much on the restrictions that it seems like there's a lot more restrictions than there are. In reality, most functions that you deal with are going to have a domain of all real numbers. What about multiplication? So let's look at kind of a concrete example. How about f of x equals 3x? So that function says multiply your input by 3. Can I multiply 3 by a negative number?
Yeah.
Can I multiply it by 0?
Wait, no.
It's just 0.
No, but multiplication itself is 0. Oh, yeah. No.
So all I want to know is if I can multiply 3 by 0 and get a number. Do you get a number when you multiply 3 by 0? Yeah, you get no discriminating against 0 is allowed in this classroom. Everybody wants 0 to not actually be like a valid number. It totally is. It's like the difference between undefined and 0 is like it's subtle, but it's like if I asked you how much money was in your wallet and your wallet was empty, you would say there is no money in my wallet, right? That's like having $0 in your wallet. If I asked you how much money was in your wallet and you didn't have a wallet, that would be undefined because you can't even answer the question, right? Like you can't, because the question doesn't make sense if you don't have a wallet. So like that's what undefined means, is that like the question itself doesn't even make sense in order to apply the operation. Whereas like getting 0 just means you end up with the quantity of 0, which is one of the most important numbers in all of numbers. So multiplication is defined for all real numbers because we can multiply by 0, we can multiply by negatives, we can multiply by positives. I know this is getting redundant at this point, but we'll get to something exciting here in a second. Maybe we won't get to anything exciting today. We only have 5 minutes. Okay, let's talk division. So there's 2 ways of thinking about division. So multiplication is what we call commutative, which means I could do 3 times x and x times 3, and it's like the same exact thing, right? So we don't have to talk about them separately. But division is a little different because x divided by 3 and 3 divided by x aren't the same operation, right? So we kind of have to think of division in 2 separate operations. One is the numbers that we can divide. So this is like, if you're thinking of division as like a fraction, that's the numbers that are in the top of the fraction. So for example, f of x equals x divided by 3. So we're dividing our input by some number. Can I divide a negative number by 3? Can I divide a positive number by 3? Can I divide 0 by 3? You can, right? If you have 0 cookies and you have 3 friends, all of your friends get 0 cookies. It makes sense to say that the quantity of cookies they get is actually 0, right? The question still makes sense. And so this is in fact defined for all real numbers as well. I'm going to stop there right before we get to the interesting stuff. Like I said, oh, well, you weren't all here when I said it, but